Okay, so did you think about an example of a negative feedback? We talked about a positive feedback where we increase the temperature because of greenhouse gas increases. You increase water vapor because warm air holds more moisture, and water vapor is a greenhouse gas, so that traps even more thermal radiation and the temperature gets even warmer, which increases the water vapor more. And so when an initial push gets bigger and bigger in the system, I'm using words like system, which you have to think carefully about, and that's called a positive feedback. Negative feedback is where an initial push quickly gets damped out. Okay, so let's leave it there, but if you have questions and you think you're old enough to follow this further, you message me and I'll answer it, okay, as a podcast or as a special message to you. Okay, so let's move to greenhouse gases. We said Earth has a greenhouse effect, a greenhouse blanket, and that happens through greenhouse gases, which are transparent to incoming shortwave or energy from the sun, so they don't get disturbed by them. Light goes right through, energy goes right through in the shortwave, but they are sensitive to thermal radiation, which is at a different wavelength because we cannot see it. I can see light outside, but I cannot see the energy coming from my skin, right? Or I cannot see in the dark. And so without a light or something. So that's thermal energy, and these molecules, there are others as well. Let's consider the main ones: water vapor, nitrous oxide, carbon dioxide, and methane. These are greenhouse gases because they trap or they absorb some of the thermal energy that is trying to escape the earth, and these are in the atmosphere. Thermal energy is mostly coming from the surface. Some is also coming from these molecules themselves. Why? Because once they absorb the thermal energy coming from the surface, they get excited, they get warmer, and they begin to emit thermal radiation just like our body is, and that energy is in every direction, right? So some is going up into outer space, some is emitting down towards the surface, as we said before. And there are some details as to why these are greenhouse gases and not the other ones. What are the other ones? Obviously N2, nitrogen, which makes up almost 79% of the Earth's atmosphere, and oxygen, which makes up quite a bit as well, up to 20% or more, are not greenhouse gases. And that's a good thing, because otherwise all the energy could be trapped and we would be hot like Venus. Remember, on Venus there is a greenhouse effect which makes it very warm, because some kind of a feedback, positive feedback happens. We said Venus is closer to the sun, but it's not so hot because it's receiving so much more energy compared to Earth. It's hotter because it's taking the energy coming in and bouncing it around. How do we bounce the energy around? We'll see in a minute, but you already know the answer. If you are living in a cold place, or when you sleep, if you are using a blanket, you're using the blanket to make yourself warmer. How do you do that? There is no heat coming in. You're trapping your own body's heat to make yourself warmer. So some energy is produced by your body because you ate all that food. So body is maintaining a temperature that is emitting thermal energy. That thermal energy can be trapped by the blanket, like the greenhouse effect, and make you warmer. So this is what happens in the real world as well. So methane is, you can think of ways in which these are produced. Carbon dioxide is produced by burning many things, naturally or artificially: coal, petrol, natural gas, vegetation, wildfires, and we breathe CO2. We breathe out CO2 as well. Plants take CO2 and make fruits, vegetables, trunks, leaves, everything. So they keep some carbon, but they also respire, they also breathe, so they also produce some CO2. And CO2 is now the most abundant greenhouse gas, and H2O is produced, of course, from evaporation, from all the things we do. We breathe out some H2O as well, and plants lose some H2O as well when they open the stomata to capture the carbon dioxide to do photosynthesis, which you may have learned of. They lose some water vapor. That's called evapotranspiration. If you don't know, don't worry about it. Okay, methane is produced, as we said, from rice paddies, from cows, things rotting like landfills where they dump a lot of waste, trash, and that can begin to decompose and produce methane. It's not the decomposition, there are processes, I'm just using the word loosely. Nitrous oxide can come also from agriculture and other ways. Okay, so these are the greenhouse gases that we have to see. And what do? We say we are causing global warming. What does this mean? That means we are constantly increasing greenhouse gases and trapping more thermal energy and making the earth warmer. The atmosphere gets warmer, land gets warmer, and there are consequences. When it's hot, we are not comfortable, crops die, vegetation is affected, many pathogens can actually grow when it's warmer. So in the greenhouse we saw plants grow better when it's nice, warm and humid, like the rainforests in the tropics, right? All these things are related to each other. Okay, and what else do I want to say about it? We want to then consider the energy balance again. So let's look at the albedo. This is the albedo. As I said, it goes from 0, where all the energy is absorbed, no reflection of the sunlight, and 1, where almost all of the energy, well, all of the energy is reflected. So you see that cold places here, Greenland is very reddish, which means it's reflecting most of the sunlight. Why? Where is Greenland? It is at very high latitude. What does it have? It has a lot of glaciers. We'll talk about what glaciers are later. Glacier. It's not just ice, it's glacier. And Antarctica here in the south has lots of glaciers, and also has sea ice, which we'll also talk about later. And the Arctic also has some colors with 0.6, 0.5 or so, and you can see a lot of the land and the ocean have much lower albedos, so they are keeping most of the sun's energy. So the net energy balance depends on how much of the energy from the sun is retained by the earth and how much is reflected right away, and the retained energy is gone into heating things. So here is the incoming shortwave or sun's energy. Some of it is absorbed by the atmosphere. There are some things like dust or some gases that can absorb these shortwave energy. Some of it is reflected by the clouds and other bright things like black carbon. You know, when you burn coal, you produce these particles of carbon which can absorb sun's energy as well. And reflected shortwave is combined with what is reflected by the atmosphere and what is reflected by the albedo on the surface as well. So deserts here in the Sahara and the Middle East, Pakistan, Afghanistan, Iran, northwest India into China and Mongolia and parts of Australia all have higher albedo than vegetated regions like the rainforests here, Amazon rainforest here, and so on. Okay, so all that together is reflecting some sun's energy from the surface. What happens? That absorbed energy is going to be used for heating things. So here emitted by the lower atmosphere, so you are talking about now energy that is trying to go out. So here is the emitted long wave energy out to space, which is a combination or the summation or the total of that long wave or thermal energy that is emitted by the atmosphere itself, like the warming greenhouse gas molecules are going to radiate energy like the hot iron in the fire of the blacksmith. There is going to be some energy coming from the surface, right? So atmosphere itself is absorbing some of the energy coming from the surface and radiate it back or emit it back, as we said. This is the critical part. This is why global warming happens. If the greenhouse gases absorbed the thermal energy and only emitted upward to space, then maybe all that energy would be lost. But they emit in every direction, which means also downward. And what is emitted, thermal energy emitted from the surface, can escape straight to space because there are some gaps in the window, in the greenhouse gas windows in the atmosphere, which allows the radiation from the surface goes straight to space. Okay, looks complicated, but think about it. We are only worried about how much of the thermal energy is ultimately escaping to space, because that's what determines the balance of the incoming short wave and outgoing long wave. That's what determines the global mean temperature, right? And that outgoing long wave is related to what's directly going from the surface to space, what's getting absorbed and bounced around, bounced back to the earth, warming the earth more, and earth emits more, and so there is some circulation of the energy happening, just like it happens within the blanket, right? This is a blanket, it's a greenhouse blanket, right? And what goes out. So you have radiation from the sun bouncing around and some escaping, some absorbed by the system, and similarly thermal energy being emitted by the atmosphere, by the surface, some escaping directly, some bouncing around. Okay, very simple actually, we didn't say too many things. Can we estimate the numbers? So incoming solar radiation, there are satellites, they go outside and measure how much energy per unit area, per square meter or square foot, how much energy is coming in. That is 340 watts per meter squared. Is this a constant number? Remember, it can change because of sunspots, it can change because of changes in the orbit, but at the present time, on average, we are getting 340 watts per meter squared. 23% of that 340 watts per meter squared is absorbed in the atmosphere, because there are things that absorb solar radiation like black carbon. 29% is reflected. I said 30% is the average albedo of the earth, and that is 29%. Is this albedo constant? Think about it. Of course not, because as global warming happens, we will melt some of the glacier, will melt the ice, will melt the sea ice, will melt the snow, so we will make them darker, which means we will keep more energy and the albedo becomes smaller. So we have to worry about that as well, but just remember 30% as the number for the average albedo of the planet. So if you average this entire thing over all of the sphere of the earth, then you will get 29% or 30%. Okay, so 48% of the energy from the sun that is coming at the top of the atmosphere is absorbed at the surface. 23% is absorbed in the atmosphere, 29% is reflected. Obviously this adds up to 100%. What's happening to the long wave radiation? So the 48% that is from the sun is doing various things like heating and evaporating. So evaporation is producing 25% of the energy to the atmosphere. 5% is from something called convection, which we will talk about in a little bit, and 17% is the net thermal radiation, or directly resulting from the temperature of anything that is emitting thermal radiation. What is evaporation doing? Evaporation is basically taking water molecules from the surface, ocean, or the water in the soil, lakes, and so on. And it can also evaporate the glaciers and snow and so on, which is slightly different process. So that evaporation is basically taking the energy from the water molecule and putting it in the atmosphere. How? Remember, water molecule has hydrogen bonds. If you don't know, don't worry about it. Water molecules are tied to each other with a certain chemical bond, which is energy. Evaporation breaks that bond and takes the energy of that bond and puts it in the atmosphere as water vapor. Why is that energy? Because when clouds form, that water vapor condenses. If there is just water vapor, which there is always some, you cannot see it. It's a gas, right? But when it condenses, it forms clouds and you can see it. But what happens when it condenses? It releases that energy. So you had latent heat of evaporation, which is the energy that it took to cause evaporation. If you don't know what that is, don't worry. Just remember that some energy is taken out of the water when it is evaporated, and that energy is released back into the atmosphere when water condenses to form clouds or to form rain. Hence, evaporation is an energy loss from the surface where evaporation is happening, and it's an energy input into the atmosphere where condensation is happening. Beautiful, right? So convection is something where, imagine now the pot again that we had on the stove. The pot begins to warm. What does the water do? As it gets warmer, warmer water is lighter. Think about it. Is the density of the water heavier, larger when it's colder or when it's lighter? If you don't know, you can Google, ask your mother, your older brother, sister, and so on. It rises. Or you can do an experiment where you take a transparent pot with the help of your mother or brother or sister. Don't do it by yourself. It's dangerous to play with fire and heat. And you can watch as you heat, water molecules will begin to rise and sink. If they rise, they go to the top and then they sink somewhere, so they begin to do this kind of circulation, and that's what happens when you warm the surface. The air near the surface gets warmer, warmer air gets lighter, and that air rises. So that's what is called convection. Okay, so let's leave this here and we'll come back. Oh, there is convection. I have got a figure for it. Again, I took it from Encyclopedia Britannica. Hopefully they allow me to use it. So here is a pot, it's closed, and there is fire here, and you can see warm water in red is rising. It hits the top, it sinks again, rises, sinks, rises, sinks. So you set up these kind of circulation. This is called convection. So cool molecules sink, warm molecules rise. Eventually you will make all the water the same temperature, or you will reach such a high temperature that it begins to boil and begins to release water molecules from the surface, and water vapor begins to build. Pressure can increase. This is how the pressure cooker works, right? When the pressure cooker begins to blow a whistle, next time your mom is cooking, you listen to the whistle. When the pressure increases, that water vapor tries to escape the pressure cooker, goes through a narrow hole and makes a whistling sound. It tells your mother that it has reached a certain stage of cooking, and she knows how many whistles are needed for the cooking to be complete. Okay, so lots of concepts, but listen carefully. And these podcasts are getting a little bit longer. Instead of 10-15 minutes, I'm going to 20 minutes, but it's better to explain them together instead of splitting them in the middle. So be patient, listen to them, look at the figures, do your Google search, ask questions, and try to learn. Okay, so we'll meet in the next podcast, and we will talk about how rising air and convection work in the real world, in the atmosphere. Okay, should be a lot of fun, right? Okay, see you in the next podcast.